internal resistance of a battery. Now, this is again one of the most misunderstood topics. Internal resistance plays an enormous role in how your car operates, for example, or what happens when you have a situation where something funny is going on with a battery of any sort. So here we go. So what I really need to do here is I need to talk about a perfect battery and a real battery. So the question is, what is a perfect battery? So when I think of a perfect battery, what we really mean here is that we have a box. And let's say that this is our box right here. And let's say I'm going to color this in yellow. And what you're going to see here is that there is a positive and a negative terminal to the battery. So in other words, there's a negative terminal, and then there's a positive terminal. And the positive terminal, you typically see a plus sign, and the negative terminal, or the ground, is at the low potential here. So I'm going to say that this is A and this is B. So this thing has an EMF. Now note that this is not standard notation the way I'm writing it, but I refuse to write the notation that they use for EMF. So what they use typically for EMF is they say that's a voltage right there. Well, remember, this is just what? This is the chemical potential. Okay, and the chemical potential is an incline that moves charge from one side to the other. So when you look at a battery, what do we see? What we see here is that there are two terminals. Okay, now let me do this the same size. So there are two terminals. And this is how we label them. So then I have my source again in here. So I have my source, and I have my minus, and I have my positive. And what does the positive do? It goes to the positive terminal. And what does the negative do? It goes to the negative terminal. Okay, and that guy is my negative. So I could call that A and I can call that B. So this is literally a pure EMF. But that's not what really happens with real batteries. A real battery has something called internal resistance. So what that means here is that when I look at a real battery, okay, it does have a terminal A, it does have a terminal B, which is negative and positive, but when you look at the inside, there's something there. So when I look at the inside, what I see here is that there is an EMF. Okay, there is an EMF, and then there's this thing called internal resistance. So I look at this guy, and this tells me here is that I do have my EMF, but I also have this thing called internal resistance. So every real battery has this internal resistance. So if you look at a real battery, then we play the same game. So I have two terminals. And so when you look at your car battery, there is a terminal like that. But all batteries have an EMF and internal resistance that looks like this here. And so, of course, that's the positive, that's the negative, and you can see that we have this EMF like that. So now it's really important that I label these points A and B. So now, what do I see here? So what I'm seeing here is that I see this. Perfect batteries have no internal resistance. So that means here is that R internal is equal to 0, which then means that the voltage at the terminal points, VAB, must be the same as the voltage of the EMF. So it's important to realize this is at the terminal points. But that is not true for a real battery. So a real battery or real batteries have, right? They have internal resistance. Which of course implies that the internal resistance is not 0. And a battery, I mean, its internal resistance is tiny. But that little tiny internal resistance plays a huge role in what happens in a battery. So now we got to look at the terminal. So what actually happens here? So what you're seeing here is that if I look at the posts, what this tells me here, now let's be careful here. So this is at the terminal points, the positive red and the negative black. And you could see here is that picture-wise, it has to be what? It has to be the voltage of the EMF plus the voltage across the internal resistance. That's what has to happen here. Ooh, I'm sorry. I wrote that incorrectly. Okay, I wrote that incorrectly. So I have to go back and delete this. Okay. So the question is this. It's the EMF. What this guy does is that this supplies pure chemical potential. All of the energy comes from the EMF. So what happens? Then the EMF distributes it to the post plus the voltage to the internal resistance. Okay, and so what you're seeing here is that this is what I said before here, and I'll write it again. This is the voltage at the posts of the battery, which implies this is the net voltage seen by the car. Maybe I should put that quotation mark there. Okay, that's the net voltage seen by the car. And then this guy right here, this is the electrical potential energy lost due to heating of the internal resistance. Okay. So when we talk about the battery, Okay, so when we talk about the voltage of the battery, this is what we mean. The voltage of the battery is the voltage measured at the post plus the voltage of the internal resistance. This is what we call what the EMF does right here. Okay, this is what we have right there. But what I want to do here, it might be easier to think about this in the language of energy. So visualization looks something like this. So let's switch to energy language. And here's what we see here, is that I know that all of the energy of the EMF must come from gas, right? To operate your car, you need gas. If you don't have gas, I'm assuming a non-electric car, and then part of that energy of the gas goes into the energy into the battery, plus the energy of everything internal to the car. Now, if I focus just on the battery, okay, so this would then be the internal resistance. So when I look at this thing, here's what I'm seeing. I have the energy of the battery, of the EMF, right? Here's the energy of my EMF right here. And that has to, I cannot have more energy than this. This has to be a constant. Otherwise, I would violate conservation of energy. So most of this energy goes where? Most of it goes into the battery. So as it goes into the battery, all of the energy that's left over is then part of the internal resistance. So in this case, then I could now switch to a voltage statement. And the voltage statement clearly says here that when I draw this picture, what I draw here is not in the language of energy, but I draw it in the language of voltage. So the voltage of the EMF supplies all the voltage to the battery, plus the voltage to the internal resistance that's lost due to heat. So then that has to be the case. So here we go. When a car is started, oops, not starter, started, current flows through the battery, right? And that means here is that now I have current through the internal resistance, which results in heat loss, right? So the battery is heat lost. So therefore, what you're seeing here, because of this heat loss, this implies less energy goes to the rest of the car. And like I said here, this plays a huge role. So when I look at the voltage of the internal resistance, this is going to be I internal times the current of the battery. So this, of course, is proportional to the current of the battery. So what I want to do here is that I want to go in and start talking about what actually happens in a car battery. So remember, this is a very conceptual question. And here we go. So now what I want to do here is that I want to explain the importance of internal resistance to cars. 4 cars, not 2 cars. 4 cars. Okay, so there's a lot of misleading stuff on YouTube. You see that and you literally go like, good God, these people really don't know what the hell they're talking about. Okay, so let me try to explain so that you could be a little bit more clearer in how you think. And by the way, you should never trust me. If you take a battery of your car battery to find out whether it's good or not, no, you have to take it to a place. And I'll show you exactly what they do. So here we go. So here's the first thing I want to go after. Measuring the voltage of a car battery with a digital multimeter is meaningless. It's meaningless. And let me tell you why. Digital multimeters puts out a tiny amount of current. So that means here that the current through the digital multimeter is about the current through the battery, which is effectively 0 amps. But wait a minute, if it's 0 amps, then what you're seeing here, that means that the voltage of the internal resistance is about 0. So if I look at the energy, now let's look at a real battery here now. So if I talk about a real battery, what we said here is that the voltage of a real battery, its EMF is 12.6 volts. Remember, if you have a 12-volt battery, it's a dead battery. And remember what I said, you have 6 cells that put out 1.2 volts. And that's where you get that number. Okay, so now, or 2.1 volts, I'm sorry. So now let's look at this thing. So that means this is all the energy of the EMF, right? I can't have more, I can't have less. So that means here, so if I look at the voltage of the internal resistance, well, guess what? It's 0. So that means what you're going to measure with your meter is that the voltage of the battery, which is now the voltage of the EMF, is not going to read the voltage of the digital multimeter, which will be about 12.6 volts. So by doing this, what this tells you here is that this implies you have a good battery. Wrong. That is not correct. And this is what really happens here. Now, if you look at cars, so here we go. So here's the second piece that I need you to understand. When a car starts, there is a huge surge of current. A huge surge of current by the battery. And you're going to see that it depends on the car. I'm going to say that, I might be on the high end. I'm going to say that it's going to be somewhere between 400 to 1,000 amps. Now, I know that the big trucks are at 1,000 amps. The car that we have, which is a Honda Pilot, puts out about 400 amps. So can a smaller car, put out less current? Yeah, probably. It could be 300. So here's what we want to do here. Now, because this current okay, apparently I got a bad internet connection. So what I'm going to do here is that I'm going to stop my video, and I apologize, but I am having problems. So here I go. I'm going to turn off my video to try to conserve. Okay. So now I'm going to go back and share my screen. So what I was saying here is that because this current is so huge, the internal resistance plays a large role in the battery performance. So here we go. Now, here's what I want to look at. So car resistances, internal resistance, can be very, very, very small. A bad battery will develop in internal resistance around 3 milliohms. This starting current creates a voltage drop across our internal. So what does that mean? So the voltage drop of car internal, the internal resistance, should be the internal resistance times the current of the battery. But look at the numbers here. So this would be 0.003 ohms. And let's say that we choose a car battery that has 500 amps. All of a sudden, this is 1.5 volts. So if I look at this thing, look what happens now. Okay, here's what you find. So that's what it is. Now let's look at 3 here. The minimum voltage, maybe I should draw that big because I want it to stand out. The minimum voltage required to start the starter is 12.4 volts. You need a minimum of 12.4 volts to start the car. Now, let's look at the picture. So here we go. So if I look at the picture, here's what you see. So the bar diagram shows this, that the EMF really is 12.6 volts, right? That's the EMF. Come on, man, my machine is screwing up. I don't know what's going on here. Am I still here?
I can hear you, Carlos.
Are you guys able to hear me? Okay, sorry. I guess I apologize. My machine is really screwing up with me. So let me try this again. So the minimum voltage required to start, so the EMF is 12.6 volts. We need a minimum of 12 volts. But look what happens now. What happens here is that if I look at the starting voltage here, right, the internal resistance here, what you're seeing here is that this guy is that amount. So that means that the voltage has now increased of the internal resistance to 1.5 volts here. So that means that this is the voltage at the terminal points. So all of a sudden, the voltage of the battery is then going to be 12.6 minus 1.5, which now gives you 1.1 volts. So what that means here is that this battery will not start your car. And the reason why it won't start your car is because it's below 12.4 volts. So since the voltage of the battery is equal to, in this case, 1.1 volts is less than 12.4 volts, right? That's a no-go. It won't work here. However, a digital multimeter read that the voltage of the battery was equal to the EMF, which was 12.6 volts. So you would have said, hey, my battery's good. That's not the way it works. Okay. So the internal resistance changes everything. Now, if you turn on, let's say that you have your headlights on. As an example here, let's say that your headlights are on, but the car is turned off. Okay. Now, what you do here is that now you turn on your car. What happens to the headlights? What you see here is that they dim. And the reason why they dim is because when the car is not running, it has an EMF of 12.6 volts. So therefore, the headlights are getting all of the current of the 12.6 volts. However, when you first start your car, the internal resistance now shoots up. And as a consequence, it reduces the amount of current that you're actually seeing. So therefore, the voltage drop across the headlights is really small here. So there's lots of other examples here. And what I'll show you here is that it looks something, I'll look at something like this here. So one of the things that, so I want to look at some conceptual examples. And I'll look at two of them. So the one thing here is that it turns out that my dad was a diesel mechanic. So I'll say here that my dad was a mechanic. So if he was a mechanic, he obviously spent a lot of time working with cars and big diesel trucks. And so what happens here is that shorting a battery is extremely dangerous. And you should never, ever do this. And the reason why it's so dangerous here is that the internal resistance heats up so much that it boils the acid. And if it boils the acid, you could then get pressure buildup that might explode the battery. Okay. And this is something that you should never, ever do here. That being said, there are people that do it. And my dad did something, a long time ago that kind of blew me away now that I have way more experience. And this is what he ended up doing here. What you're seeing here is that this person is going to short out a battery. In fact, there's two batteries here. So he's going to put a wire across these two batteries, or just one battery really, and look at what happens here. Okay, here it goes. Yeah. Do you hear him laughing? It's because he's nervous as hell. He's scared, as he should be. Look at that. He's in the hood doing this. Check it out. You see, that's a thick wire. Look how hot it is because there's so much current running through it that it starts to light up like a light bulb, and then it should start melting. Oh, there you go. Look at that. There's no more wire. So, yeah, that battery, by the way, is now a dead battery. So if I was to come back and look at this thing here, let me do a new share. You can see here that this wire has so much current that it melts it. And starts a fire. Okay. So what you're seeing here is that, but note what this does here is that shorting a battery kills the battery too. It literally kills the battery here. And yeah, if you want to damage the battery, that's what you should do here. So why would this be so, why is the current so huge? And then this brings me to my second example, which is going to be my father-in-law. And the 9-volt battery. You know, my father-in-law is, he's old school. And what's interesting about him is that what he would do here, he would have change in his pocket all the time. And, he would put his hand in his pocket and then he would shake the coins around. I guess he just liked listening to the coins or something. Even though I told him, I says, people nowadays don't carry coins. But he says, yeah, I still like the sound of coins. So this is what he did here. So he was over for dinner and he asked me if I had a spare 9-volt battery. And I said, yeah. And he puts it in his pocket and I go like, that's really not a good idea. You shouldn't do that. And he goes like, yeah, you'll be okay. So this is what he did here. So remember, he has a lot of coins. So now what does a 9-volt battery look like? A 9-volt battery has a small terminal, then it has a large black terminal. And what you're finding here is that if you were to draw the real 9-volt battery, here's what you see. This right here is the 9 volts. This right here is the ground, right? So in other words, this is the plus 9 volts. This is the 0 volts. Right? Again, that's the positive, that's the negative here. So if I look at this thing and I look at my battery, we know that this is the case of my battery. And so then if I draw this out, I have a voltage source here. I have an internal resistance here. And it looks like this. So this guy is the 9-volt battery. And this guy has an internal resistance of 1 ohm. Now note, that is not true. The internal resistance is not 1 ohm. I think it's less than that. Okay, but let's say that's what it is, just to make the numbers easy here. So now let's look at this thing. So what does my father-in-law do? He decides to put this in his pocket. And now we have the coin that made the connection. So now what you're seeing here is that this is a coin. And I tried to measure the resistance of the coin. And what I found here, I couldn't measure it, but it's approximately 0. So I'm going to say that it's about 0.3 ohms. Note that the coin has more resistance than the internal resistance of a car battery. So look what happens. I now have a conductor. And look it up here. You could see that this thing is going to turn red hot. So what happens now? Now I'm going to have current flow through the coin. So when I look at this, I see that the current of the coin, according to Ohm's law, is going to be the voltage divided by the internal resistance of the system. So look what happens now. What happens here is that this is going to be 9 volts divided by 1 ohm. This is 9 amps. This is a huge current. Huge current. So if you don't think this is not huge, then what we do here is that the battery now dissipates power. Okay, it dissipates power and gets hot. The question is how hot? So now if I look at the power, the internal power is going to be the resistance of the coin. Nope, not the resistance. The internal resistance is what we're calculating, times I squared. And so what you're going to see here is that this is going to be 1 times 9 squared, which is 81 watts. Now, if I just go to 1 sig fig, this is a 100-watt bulb, right? This is the heat generated by a 100-watt bulb. I mean, and let me put it to you this way, 100-watt bulbs. Well, guess what? They used to use them. They used to use a 75-watt into those little kitchen ovens where you could bake little small, cakes and stuff like that. So the internal resistance plays a huge, huge role here. So what ended up happening with my father-in-law is that the battery, the 9-volt battery, got so hot it burned its form into his leg. So you could imagine we're at the dinner table eating, and then my father-in-law with his wide-ass legs is jumping around because the battery is so goddamn hot. And oh my gosh, I laughed my ass off. And my wife got really pissed at me for laughing because he was in pain. And you know what? He's a dumbass. He shouldn't have done that. I warned him not to do that. And this guy's a technician, an electrical technician. And oh my gosh, it was funny as hell. So what I want to do here is that I want to finally draw a picture of the battery, a real battery, and then leave it right there. So now what I want to do here is that I want to draw a circuit diagram of a real battery and a single resistor. So we did it for 2 resistors. I mean, with 1 resistor before. Now I want to do it for 2 resistors. So let's do this. And I'm going to put in numbers here now. Why? So it's a little bit more clear. So here's my setup. I'm going to have a battery. So here's my battery. Okay, this is my battery. And then it's going to be connected to a single resistor like this. So if I look at my battery here, we know that that's the full battery. I can't separate the internal resistance. So I know that I have a source, and then I know I have internal resistance here. So I'm going to say that this is my EMF, and I'm going to give it numbers of 12 volts. I didn't have to do 12. I could have done 10. That would have worked too. And then I'm going to exaggerate the internal resistance so that it's 2 ohms. And then this is my battery. This is A. This is B right there. So then I'm going to say that this is my load resistor, which is 4 ohms. So what does this mean here? What this means here is it means this, that if I apply Ohm's law, I could see that the voltage of the EMF is going to be the voltage of both the series resistance of the I current of the battery, right? So now I attach it. So what's going to happen? I'm going to have a current flow of the battery now. So when you look at this thing, this should be the internal resistance plus the load resistance to give me I of the current of the battery now. So what this tells me here is that now the current of the battery has to be the sum of the resistances divided into the voltage of the EMF. So when I see this, I'm going to get 4 plus 2 divided into 12. So then I'm going to get 2 amps. So what does this mean here? Well, picture-wise, what does this say? What this says here is it says this. I have an EMF. I have this much for the EMF. And according to this, this is 12 volts. I can't have more than 12 volts. So that means here that number has to be a constant right there. Now, how much goes to the internal resistance? Well, if I look at the voltage of the internal resistance, it should be I internal times I of the battery. So this guy should be 2 times 2, which will then give me 4 volts. So in other words, the internal resistance has an internal drop of 4 volts. Now you can immediately see that the voltage across the load resistor has to be 8, but let's just calculate it. And this is across the load. So this is going to be the resistance of 4 times 2, which then gives me 8 volts. But we already knew that just by looking at the picture. So we know that this is that of the load, which is 8 volts. So what you're seeing here is that the load does not see the full 12 volts. It's seeing only a piece of it. So now if I draw the diagram that I really want to draw, it looks like this here. So I have my battery. Okay, so let's draw my battery. My battery looks like what? It goes like this. And then I have my source. Then I have my internal resistance. And I'm going to say that this guy right here is the battery. Okay, so this is my point B. This is my point A. Okay, so now I know that this guy right here is 12 volts. And I know that this guy here is 4 volts. So remember, I should have colored this, right? I should have colored this because I want you to know that this is a package deal. It's not like I can separate the internal resistance from everything else here. That is the battery. And then I have this other resistance, which is the load. And we see that this drop was 8 volts. So when I look at this thing, what I'm seeing here is that this is my circuit right here. So what do I see? I have current. Current comes here, current comes around, and then it comes back here. And we know that the current of the battery is 2 amps. So here we go. Now let's look at the potential picture. So what do I know? So if I look at the potential picture versus position, I see that wires, remember wires, okay, remember the voltage across a wire is 0. So you can see here is that I come here, and then I come here, and I'm just looking at the resistor part. And then I have this guy right here. Okay, so I outlined the 3 elements. Here I go. Look at what happens. Look at that. I'm here along the wire, right? And then what happens? I have a climb up to 12 volts. So let's say that this right here is my climb of 12 volts. So what does the EMF do? It takes a charge, takes a positive test charge, and it moves it up the hill. So then what happens? You could see I go through a wire now, and then I see the resistance. And so what happens? Part of this, a third of this, is a drop due to the internal resistance here. So when you're looking at this thing, you could see that this is the drop across the internal resistance. So that means here, from here to here, that's an increase of 12 volts. So the charge gains electrical potential energy. Now the charge is doing what? It's moving down the hill and it loses electrical potential energy. And so when you're seeing this, this is the flat. So then I see from here to here, this thing dropped the height of 4 volts. And then when I hit the load resistor, you can see that this is another drop right here. So then the charge again does what? It loses electrical potential energy, which in this case is transferred into what? It's transferred into heat. So then this guy dropped a voltage, a height of 8 volts. And that's the role of the internal energy. Huge, huge role in everything. So what voltage does the load see? So the battery, so what you're seeing from this picture is that the battery only puts out 8 volts, not 12 volts, right? It puts out 8 volts, not 12. And that's because of the internal resistance.